to recap what we had done last time, okay, we looked at the incremental encoders. They're optical encoders, and what we saw was that we could do 1x position decoding and we also saw the circuit for doing 4x position, what is called quadrature decoding. Okay. Then we looked at velocity measurement, and first thing that we looked at was tachometers, tachs, which are basically DC motors. Then we also looked at frequency to voltage converter based, okay, using incremental encoders. We also looked at software based velocity estimation. Okay, we briefly touched upon acceleration sensing, pointing out that there would be only a few circumstances where acceleration sensing is likely to be used. Then we moved on to the external state sensing, and in this we started to see tactile sensing. Okay, here we looked at proximity rod based sensor, we looked at photodetector based sensor, and we looked at the conductive elastomer. Okay, so we can start out by just going over the last thing that we did, because that was done in a little bit of a rush. If you look at the diagram that I had shown you last time, dealing with the conductive elastomer, what you have is a protective layer which is in the front, followed by the conductive elastomer. Now the property of the conductive elastomer is that when you compress it, the resistance decreases, okay, and it is local because it's not a very highly conductive material, so local effects can remain local. And what you do is you have a PCB, printed circuit board, in the back with some electrodes as shown here. You have a inner part of the electrode which is shown as dark circles, and then you have an outer ring of electrode, and you have Y direction, you have all these electrodes, and in the X direction what we do is we connect the sensing part. So this X line that is shown here will actually be connecting the center portion of this through a diode for these also. So this X line connects to all the X direction center spots. Similarly, the second X line will connect to second row of all the center spots. So by dividing this array into X and Y directions, what we do is, if we activate one of these transistors, let's say, when you have a pull up resistance here, and you have, depending on the resistance of the polymer elastomer that is there, the contact between these two will be made to some extent depending on the resistance in between them, and that resistance will depend on how much pressure is coming at that particular spot. So therefore the output from these X lines will change, and we scan it by powering one of them at a time and scanning each line individually. So therefore the X and Y location completely tells us which of the electrodes are having how much resistance in them, and therefore we have a map of what the pressure that the gripper is putting on the, or the object is putting on the gripper. And this is what the basic idea about tactile sensing is. Okay, now let's move on to different types of, some more types of tactile sensors. We have, this was developed by IBM, it's called pneumatic switch based. Okay. Basically what it consists of is a flexible skin So I'm showing it here. It's a rubber type of skin, underneath which there is a thin metal diaphragm. So the thin metal diaphragm is shown here, and then you have the support structure, and there are electrical contacts jutting out. So this being all support structure, I am shading that in the with hash lines. What is done is you pressurize this chamber. Pressure is applied to that, so that in the normal positions, because of the pressure, this disc, which is in a curved shape, is part of the metal diaphragm. It can have two stable positions. It can be up like this, or it can be down like this. So if there is an object, supposing there is an object here, and we continue our flex skin here. So what I am showing is that instead of it being up here, now because of the object, it's been pressed down and it's in the other stable position, and the metal diaphragm which is behind this is now making contact with the contact that we have. So these contacts will all go to some electronic circuitry, and this is our contact here and here. And so because the object is there, the skin has been depressed. This is the flex skin that's been depressed, and because this is a metallic disc which is like a dimple, you must be familiar with the fact that if you have a round disc with a curvature like this, and then if you press on it, then it can take a stable position which is going to be curvature up from curvature down. Okay, so this is what is happening. This gets into a down position, and then it makes a contact, and that contact can be read off. So therefore we know in exactly which locations the object is causing it to deform and make contact. Now the task of the applying the pressure here is obviously to make sure that when the object is removed from there, this pressure is sufficient to make the disc go back into the original position. Okay, let's look at another one It's called anisotropic conductive rubber based. Okay, what you have here is you have a conductive, this is anisotropic, meaning it has conductivity in one direction but doesn't have conductivity in the other direction. So assume that this is conductivity coming out of the paper, coming out of your board, and what you do is you segment this so that there are strips of conductive material put together. You put it on nylon strings, and then you have underneath this you have a metal track. Track is running along the direction that I have shown you, and this is of course mounted on some PCB. So this is our printed circuit board, right? So when there is no load, then you have this situation. What is to be recognized is that this cross section that I am showing here is basically that rubber conduction is perpendicular to the copper tracks. Okay, in the PCB. Now supposing we apply some moderate load on it, then what happens is this conductive rubber deforms and assumes a shape like that, and it's kind of restrained because there are these nylon insulating. So it will start to make some contact, and if I look at the image, you can say, of each of this width and the distance between tracks on the PCB, then you get a grid, and here there are no contacts at all. When you come to this situation, then there is some amount of contacts developing because of the pressure which is being applied on the elastomer, on the conductive rubber. If you put heavier load, then this rubber deforms to make much more contact. So this is our nylon ropes, and then we have the PCB, and so the kind of image that will be generated here will be making contact in bigger areas, and therefore the resistance between a electrode put on the top of the rubber and at the bottom in the PCB will change. And once again, because you have XY grid structure, you will be able to find out exactly where the pressure is coming. Yes. It is used in making sure that you have tracks which are basically okay. So actually you don't have to separate this. What I am showing here is for your convenience to understand that current is not flowing in this direction, it is only flowing out of the paper. So that is the basic thing. Otherwise you will have to make separate strips and you will have to join them together. So then epoxy, etc., wherever, whichever you use to join it, will create a problem, and therefore this anisotropic property is being used here, that the current flows in one direction. Its preferred direction is out of the board, not across the paper. Okay, we will look at one more tactile sensor based on piezoelectric property. It's polymer type of piezoelectric. Tactile sensor. Okay, and basically it is based on what is called PVDF, polyvinylene fluoride film, which is a good piezoelectric material. Good in the sense that it generates fairly large electric potentials, okay, when it is subjected to pressure. Okay, the basic construction of this is somewhat similar. What we have is, once again, you have a protective layer, then you have the PVDF material, and in this PVDF material we deposit some metallic tracks. So you have these metallic tracks, okay, underneath. So this is of course on sheet here. Then underneath you have a silicon rubber sheet, and what you do in this sheet is you make it out of two types of rubbers. You have the silicon rubber, which is not a very good conductor, and you make holes in that and you fill in conductive rubber. So this portion here is not a hole but a conductive rubber. Okay, this is our protective plastic. This is our PVDF layer. This is the silicon rubber. Okay, we have metallized electrodes. I call them row electrodes. Okay, and then we have one more layer here, which is again insulating, and it's got holes in the same place, and these are holes, right? And finally we have a PCB which has got column tracks. Now if you look at this of course all together, and if you look at the track locations, if you put them on top of each other, the intersection is where all these circles are shown. Okay, so the basic way it will work is that when some pressure comes on this, some object is placed on this, or this is all in the robot hand, and the robot hand is holding an object, then at various places pressure will be there because of the shape of the object, and that correspondingly you will have a stretch of the PVDF layer. Because there is a hole here, this has a tendency to go into the hole, and as that goes into the hole, the PVDF stretches. Now there are both effects in the PVDF. You know, the thickness direction, the effect is small. Okay, thickness, but it is large in plane. Okay, that is due to stretch. Right, so that is the whole purpose, that you have conductive spots here, and these, when the pressure comes, these conductive spots go into the holes here, and so they make contact with the lower tracks, and consequently the PVDF layer also deforms, and that because of that bending that takes place, there is stretch taking place, and therefore there is a larger piezoelectric effect in those areas. Okay, and then of course what you have to do with all piezoelectric type of sensors is that you have to read this sensor signal before the charge leaks. Fortunately, PVDF time constant is of the order of a few seconds. So it is not a major problem, because in a few seconds we have to scan through the whole array and determine where the pressure is, and that is not too much of a problem because there is sufficient time available. If the time constant was much smaller, like in the PZT or PZT type of piezoelectric materials, then it would be a much tougher problem to be able to scan it in time for all these different spots. Okay, now let us look at another type of sensor which is quite important, and that is called a slip sensor. What we want to do is, if you imagine what we do when we hold an object in our hand, is that we adjust the pressure between the fingers so that the object doesn't slip. If we hold a heavier object, obviously our pressure has to be greater so that we generate sufficient friction force. Wherever it's a light object, ping pong ball or something like that, then you don't have to hold it that tight, because you know that if you hold it too tight you may damage it. So the same thing needs to be done for robots, because different type of objects, if they are made to handle, then it has to have some kind of a sensor which will help it to determine whether there is slipping taking place or not, right? So what can be done is, basic idea that you can have is, you have a gripper and you have some fingers of the gripper. One side I am showing a basic finger, the other side I have modified the finger to include a slip sensing device. Okay, so if you have an object, then an object will be making contact. These are objects sitting here, and what I have is, inside this cavity I have some rubber damper, on top of which I have a piezoelectric crystal, Rochelle salt crystal, okay. These are, as I said, these are rubber dampers. Okay. Then on top of this you have a spring like structure, on top of which you mount a sapphire needle. Okay, this you need to have one more damper, and that is a metal sheet damper. If you think about it, it's basically nothing but the old phonograph needle type of device. So what happens is, when the gripper is closed on the object, the needle touches the object, and then if there was any slipping taking place, then slip will causes force vibrations. In the piezoelectric material. Okay, as I say, it's like a phonograph. Record pickup. So if the object starts slipping in the gripper, then this needle is excited and it starts to vibrate. This vibration is transmitted to the piezoelectric crystal, and piezoelectric crystal will give some output which can be sensed. So if we start getting a output, then we know that the object starts slipping. Then whatever mechanism is there in the gripper to start closing in further so that the object doesn't slip. Now the problem with this type of device turned out to be that it was tending to be sensitive to manipulator motion itself. These rubber dampers are actually used for protecting it from that type of vibration coming from the robot body. However, if you make this damp a lot, then you end up killing off the signal also, and therefore the sensitivity to slip then will also reduce. So there is a trade-off, and of course, like a phonograph record needle, you require periodic replacement. Of the needle. Several improvements were made by various other researchers. So some of the improvements, improved device had steel ball, okay, instead of the sapphire needle, and of the order of about 0.5 millimeter diameter ball was used, and instead of using a piezoelectric crystal, they use electromagnetic pickup, and instead of using these rubber type of dampers, they used oil damper. So the construction of the device is a little different, but if you do these things, then it becomes much more robust in terms of sensing only the slip motion and not so much the motion of the robot itself. Yes, please. Sorry? Yeah, that is of course a that's a question of how you do the. We will talk about that. Let's talk about that now. See, basically it boils down to force sensing issue. Okay, so issue is that what should be your grasping strategy. So supposing we using force sensing, one of the ways to do force sensing would be to look at the motor current, and so if you have a armature, you connect a series resistance to it, and then you look at the voltage across that, okay, V sense, let's say, then V sense will give you an idea about the armature current, and we know that the armature current is proportional to the torque that is generated by the motor. So it could be a motor that is actually trying to close the fingers, or it could be a motor which is somewhere else in the robot. But if you talk about slip motion, then of course we have to talk about the motor which is trying to close the fingers, and that is, I am assuming, is a servo motor. Then we know that the torque is related to the force, so some kind of transmission, and maybe there will be some kind of efficiency coming in, and that means this will be equal to eta times kt times Ia divided by the whatever the transmission is, right. So we can measure a force, and then our grasping strategy could be See, first of all, offline we determine minimum and maximum force that can be applied on the object. On a part, right? So we have some idea beforehand that what is the force that can be applied. Then if you use minimum force to start with, and then increase force if slip is detected. Right? But you have to subject this to limit of max force or max displacement. We cannot allow the gripper to keep on closing, because then we know that the object will get crushed, and we can take these two up to the maximum force that will be permissible. So there will, many times it will depend on the orientation of the gripper whether the slip happens or not. So if the fingers are like this and the object is heavy and tends to fall down, if the gripper was like this, the object will not tend to fall down, right? So there could also be a more complex strategy in which you try to reduce the force wherever the slipping is not taking place to see whether slip starts taking place. So you could bring it to the border of slipping taking place and then increase the force by a certain amount. Could be one strategy. Now all this depends on how accurately we are able to measure the force and the slip. For example, in this type of force sensing using motor current, it is not going to give you perfect. It is not measuring the force actually, it is measuring the current, and therefore if you had Coulomb friction, then the current will have to overcome the Coulomb friction and then apply a force. So what you will be actually applying would be less than what the current is telling you. So this is one of the problems. The other problem would be supposing the temperature changes. Okay, if temperature increases, let's say, then your armature resistance will increase, your K value will generally decrease, and both of these effects will decrease the torque. Okay, then of course the issue of brush noise, all those kind of issues are there. Okay, but these are getting into the details of how to make this work. Basically you can apply this type of strategy for gripping. Okay, let's look at another slip sensor, which is a little different principle. This was developed in Belgrade, Yugoslavia, or erstwhile Yugoslavia. Okay, basically it consists of a softer surface at the gripper, and there is a wheel inside with this as the axis, and the wheel. So when the object is gripped, this is one of the fingers that I have shown, and the object is between the two fingers, so the other finger is above it, which I am not showing. This is my object. Now this wheel has got knurling on it, so the surface is not very smooth. This is a knurled surface. And what you do is, underneath you put a little cantilever type of device, and you apply some voltage to it, and then you put a contact very close to it, So you have applied some supply voltage and then you have a contact very close to it. If the object starts slipping, then this wheel is going to rotate. If it rotates, this cantilever strip which is engaged in the knurled portion is going to start vibrating. Starts vibrating, this will make intermittent contact. So you are going to get some kind of output voltage which is going to vary between Vs and 0 depending on whether the contact is made or not. Okay. So basically it is using forced oscillation, which is similar to what we saw in the sapphire needle type of setup, but it's much simpler in the sense it's not using any of the piezoelectric material. It is only a very mechanical action which is sensing the motion of the object. It's in direction of in the plane of the roller, right? So this doesn't have as much of a problem of sensitivity to robot vibration, but it can only detect slip motion in the plane of roller. So they improved that by another version of this sensor, in which you have, this is the same kind of soft layer, and then you have some structure here connected to the soft layer which is conductive, and you have a needle which is passing through here, and then there you have some insulator here through which the needle passes and comes out here. So this is insulator, and then you apply some supply voltage to this. If the object was slipping, then again there are vibrations induced in this whisker like cantilever, and then it will start making contact with this thing, so you will get some output of the same type. The advantage is that this could be made in 3 dimensions like this, so that if the vibrations were in the plane or out of this plane, both will have some contact at this point. Okay. So therefore you can detect slip in any direction. Right. Only thing is that this failed when you applied larger forces. Okay. Fails when force is large, and the reason for that is that this needle, being a very thin and pointed needle, digs into the object and then stops vibration altogether. So this is not extremely satisfactory also. So they came out with a third idea, in which you have this soft surface where the object is being gripped, and then you have behind this you have some kind of a housing where you put a spherical ball here, and then there are spring loaded contacts here and here. The ball is made out of conductive material, right. So basically you can recognize this as our mouse, computer mouse type of setup. This sphere is made out of conductive material, and what is done is you divide this into strips in the in the two directions, and you paint some of these squares, alternate squares in fact, by some insulating paint. Oops, that is wrong. Okay, anyway, I will continue doing it here. That should have been not colored. This is colored, this is colored. So like that, alternate squares are insulated so now you get the idea of what is happening. Right, this was not supposed to be, so this is going to be okay. So idea is that as the ball rolls due to motion of the object, you are going to get some, these will either detect conduction or no conduction, and therefore they will give out some kind of a change, modulation in the voltage, and that can be detected. And now here we have so this is got insulation patches. Okay, and so there is no vibration problem. Okay, and then of course slip in any direction can be detected. Right, so this is a series of developments over several years that some researchers in Yugoslavia did. Okay, this is fairly effective, at least the improved version is quite effective. So now let us look at force sensing. We have seen tactile sensing in the sense of where the pressure is developing in different parts of the gripper, and we have seen slip sensing, that if the object starts to slip, then we have that is detected. If you look at the, we would like to sometimes actually measure the force. Okay, as I mentioned earlier, that if you are using something else like motor current to sense the force, then sometimes you will be wrong, because Coulomb friction, temperature will change, and then what you are measuring is the current and not the force. So direct measurement of force can be attempted, and that can be done by using strain gauges. Measurement or sensing. Now basic principle is very simple, and I am sure all of you are familiar. If you take some kind of a cantilever beam and mount on it okay, you have a thin metal either it could be paint or it could be a thin deposition, and you may have a substrate which is non-conducting. Okay, this is the substrate portion here, and similarly you may mount something at the bottom also, and this is our basic setup. This is basically the foil type of strain gauge. Now of course, if there is some force coming on this cantilever, then the cantilever deforms, and this metal portion here either stretches or contracts depending on which side it is on, and the resistance, which is basically depends on the length of the strain gauge and the conductivity and the area of cross section. Now when the gauge is very thin, the cross section area doesn't change when this deformation takes place. It's mostly the length that changes, and therefore the resistance will increase or decrease depending on you contracting or expanding it. Other type of strain gauges are also possible. Other types will be, say, thin film deposition directly without using a substrate. You can deposit, you can sputter some thin films, or you may have semiconductor type, which is much more sensitive, and it's made out of by using VLSI type of technology. And for processing this, one can have a bridge circuit, and you will have some adjustments. This is our gauge, so let us call that RG. This is some resistance R1, this is a balance resistance, this is some resistance R2. You will connect this to your V supply, and this connect to your minus V supply, and that output is taken from these parts of the, and you may feed this into a operational amplifier type of circuit. With some gain that you will select depending on these resistors. So the order of magnitude of gauge resistance will be from 10 ohms to about 1 kilo ohm. Supply voltage you may choose like 5 volts or 15 volts. If you are using op amp the same supply, then perhaps 15 volts. Then these resistances have to be fairly high so that you limit the current. So something like 100K can be used here. 1 mega ohm may be used here. What you have to ensure is that RG times RB is equal to R1 times R2. Okay, and then you can see if this was not the case, then some output will develop here, which can be measured, and which will be then an indication of the strain that is developed, which will be indication of the force that is coming on the finger. So supposing we have a gripper, so this is the parallel motion type of gripper. Okay, so I have some fingers moving on some moving blocks here. Okay, similarly I have another finger here, and this is moving on some other block here. Okay, and then of course you have to have an object. So this is my object here. Okay, I will mount the strain gauges here and on the other surface, maybe inside, maybe outside, depending on what configuration I want. And then I can use this type of circuit. I can use 2 circuits like this and look at the differential output, or I can put these gauges in different arms of the same bridge, and this way I can measure the force of on the fingers more directly. Now many times you are not only interested in one component of force, this will give you force in the direction of the what the gripping force is. Sometimes you are interested in much more. You would like to use when you are thinking about assembly process, when you are mating one part with another part, and there are forces which develop because of this interaction with the environment. And when people started doing assembly using robots, they found that simple operation of putting a peg in a hole they could not do. There was sufficient clearance, there was chamfer in the front of the peg, but still they could not put the peg in the hole. Then they found that various devices of course were developed, and I think remote center compliance may have been mentioned, but another way to do is actually to look at all the forces which are developing due to the reaction force, and then corrective action can be taken. So if you look at that type of sensor, which is you can call a 6-axis force / movement sensor, then I'll try to draw the configuration of this, which is a little complex. You have basically 2 cylindrical members, this is hollow, and then you have some arms sticking out of it, and there is some narrowed portion in neck. So if I have, this is another one, cantilevers basically, and there is a neck, and then there is a bottom ring. Okay, and then there will be some other features of this, which I will tell you what they are. Basically, you mount the strain gauges here and on the back side, in here on the back side, then there are two more in the back. They will have strain gauges on both sides of the cantilever. This is not all. You have another concentric cylinder, okay. Now this one is having cantilevers which are going to be perpendicular to the one that I have shown you there, and this will be something like, now this is getting a little small, but there are features in the top and the bottom cylinder here, from which these cantilevers are mounted. So this cantilever, for example, is here, and this is a arm which is coming out from the top. Then this bottom ring here has the other part of the arm. Okay, so this is basically, I have shown part of it. Let me, okay, I am not drawing the all of it, but you get the idea that this is the portion where metal is there, and there are gaps here, right? So there is two sets of, you see the top ring and the bottom ring, they have columns. Between a column of the top ring and one column of the bottom ring, you have a horizontal cantilever here. So there are four such cantilevers around the circle here. We have four such cantilevers pointing downwards here. The basic structure of the cantilever is that it's a narrowed portion, and then you have necked portion before it's connected to the other body. Right? So this, you will paste your strain gauges here and at the bottom. Let's call this R1, call this R2. The directions are so that if you look at your axis, say this is our x axis, this is our y axis, this is our z axis, then if you go from R2 to R1, you are always pointing in the positive direction of your x, y or z axis. Okay, so here our x axis is this way, so this is going to be R1, this is going to be R2 on the other side. Okay, now positive y direction is this way, so you're going to have R2 here and R1 on this side. Right, if you look at this particular column here, then positive y direction is this way, so R2 and R1 will be on this side and this side. R1 here and R2 would be on this side. Now these columns are named. Let's say this is Py minus, this is Px plus, what is there here is Py plus, and what you have here is Px minus, which is hardly seen. Similarly, you will, because strain gauge is mounted here, you have R1 here and R2 here, because going from R2 to R1 you are in the positive z direction, right? So naming convention is consistent, and you have Qy minus here, Qx plus here, you have Qx minus and Qy plus, which is not seen, right? So With this type of arrangement, what you can do is you can connect these R1 and R2 as a potential divider. So with some voltage here and some voltage here, and this will tell you directly the deformation. It's not a bridge circuit, it's much simpler than that, because with so many strain gauges, if you start to apply the bridge circuit, it will become very complex. And so if you can simply write the expression for the estimation of force as Py plus Py minus. Similarly, Fy is going to be approximately equal to Px plus Px minus. The z direction force will be obtained from the Q sensors, Qx plus Qx minus plus Qy plus Qy minus. The movement about the x axis can be gotten from Qy plus minus Qy minus. Similarly, the y axis torque can be obtained as Qx plus minus Qx minus, and the z direction movement can be gotten from Px plus minus Px minus minus Py plus Py minus, right. So this way, with this type of structure, you can see actually what is happening. If you look at Fx, for example, we want to measure the force in the x direction. Now force in the x direction will not be given by these columns at all, because these are deforming in the perpendicular plane, whereas if you look at these, when the deformation takes place, you have x direction force acting here with respect to this part, then this is going to deform, this will contract, this will expand. Similarly, this will be affected. So these are the two strain gauges or two bridge columns where we are sensing the strain. These are the two which are going to give us x direction forces, and that is what is here. This will be simply added together, because the way we have defined R1 and R2 consistently. Okay. Similarly, the y direction force will depend on only this strain gauge and this strain gauge. Z direction will depend on all the 4 horizontal cantilevers. You simply add up the output of those. The movement about x, this is the x axis, the movement about x is this way, so you have to look at the difference between these two, and that is what is done. So basically, because of the construction, you are able to isolate different components of forces, and you can measure them. So this was actually developed by the Stanford Research Institute in collaboration with NASA, and actually it was the work of Victor Scheinman for his master's thesis to develop this type of a force sensor. I think we are out of time. So this module, basically what we have done is we have looked at different type of sensors which are useful in robotics, internal type as well as external type. There is one major external type which we have not talked about, and that is vision, and we will talk about that at length in later modules. Thank you.